Right, first question. We have two charged particles, one positive, one negative, moving in the vicinity of a current carrying wire. The arrow indicates the direction of movement of the particle. Okay, yeah, so this one is going in that direction, this one's going in that direction. Indicate the direction of the magnetic force on the particle due to the magnetic field produced by the wire. Okay, so it's not stated, but we're not going to consider the effect these two have on one another. We consider the case like that, and then like that. Okay. So let's, for the purpose of scanning and providing it as a PDF you can download, let's recreate this. So this is question 1, and I've got my wire, and I've got my current in this direction. Okay, in other words, the electrons are going in that direction. Okay, I've got a positive charge here going in that direction, and I've got a negative charge going in that direction. Okay, good. Now, so these are charged particles in a magnetic field. There's current in this wire, which means it is creating a magnetic field. And if a particle, a charge is moving in the magnetic field, it feels a force on it. And I've got to indicate the direction of that force. Now to do that, I can use the right-hand rule 3, which says that index finger in the direction of the particle's movement, middle finger in direction of the magnetic field, and then thumb, which is perpendicular to this one and to this one, is pointing in the direction of the force, if it is a positive particle. Otherwise it would be in the opposite direction. Okay, so to do that, I've got this, I've got a direction which it is going, but I don't have this. So what is the magnetic field? So that's from the first right-hand rule. So the current is in that direction, so I put, so the magnetic field is like this. It is coming out of the page and going into the page. So one field line will be something like this, going in here and then making a circle and then coming out here again, right? So from the top it would be like, you know, these circles. So by the first right-hand rule, the charge would be coming, the magnetic field would be coming out of the page, and the notation we use for that is like that. Okay, so magnetic field here is coming out of the page. Okay, so now let's use the right-hand rule. Okay, so this in the direction of the movement. Okay, so like, well, okay, I don't know, well, I'll be able to recreate it so you can also see. Okay, so it's, okay, now, well, you do it. Okay, so using this rule, you should get that it is downwards. I'm going to sprain something if I try to get it in the video frame. So the force is downwards. So that's the direction of the force. Well, let's call it F. Okay, so there we have indicated it. This one, let's try again. So for the same reason as here, the magnetic field will be coming out of the page here. Okay. So that circle with a little dot is notation for out of the page. Okay. So out of the page. Oh, well, this one is actually doable. Okay. So direction of movement. Magnetic field coming out of the page, so the force is towards the right, or it would be if it were a positive particle. It's not, it's a negative one, so the force is in the opposite direction as the thumb is pointing. So the force is left on this one. Okay, so if it's standing still in the magnetic field, there's no force, as opposed to a charge standing still in an electric field, in which case it does feel a force. But for magnetic field, it has to move in the magnetic field. If a charged particle in a magnetic field has to move in that magnetic field for it to feel a force. Okay, and that's the first question.